Hello, my name is Ashley Barker, and for the next few minutes you will learn about the heat loss term in our energy balance. For this project, we are interested in a reactor that separates water into hydrogen and oxygen, or carbon dioxide into carbon monoxide and oxygen. The goal of this presentation is to discuss the methods and results for calculating the loss fraction or heat loss term in the energy balance for the reactor. While calculating this can be done using traditional heat transfer calculations or the resistance network, I will be utilizing the text heat transfer model of a solar receiver reactor for the thermal dissociation of zinc oxide, experimental validation at 10 kilowatts and scale up to 1 megawatt by Schunk et al. In this paper, a transient heat transfer model is developed for analyzing the thermal performance of a thermochemical reactor for the solar-driven dissociation of zinc oxide in the 1600 to 2100 Kelvin range. The model includes three forms of loss: radiation, conduction, and conduction. For the purpose of this presentation, I will be focusing on only two types of loss: conduction and convection. This approach is appropriate for determining heat loss because it uses real validated experimental data in order to predict the heat loss on a larger scale. Shortcomings of this approach are that the result is a range instead of a singular value, and that the paper is analyzing a thermochemical reactor for zinc oxide instead of for water or carbon dioxide, which may affect the results as we are wanting to interpret them for this project. For the paper, a set of 4 experimental runs was used to validate the reactor model. This model was then utilized to make predictions for reactors with nominal power inputs of 100 and 1000 kilowatts. The energy balance was completed for the system, and I will discuss these results next. From the paper, Table 3 lists the energy balances for the 10, 100, and 1000 kilowatt reactors. The significantly higher predicted value for the 100 and 1000 kilowatt reactors as compared to that measured for the 10 kilowatt reactor is primarily due to a higher surface temperature, significantly higher reaction rates, and a reduction of the conduction losses through optimization of the geometry to minimize the water-cooled components. 46.7% of the solar power was lost through conduction in the water-cooled components for the 10 kilowatt prototype reactor. Optimizing the prototype reactor geometry by downsizing the size of the cavity exit from 80 millimeters to 30 millimeters and by removing the exits, water cooling yielded an improved efficiency of 16.9% and conduction loss changed from 46.7% down to 22.1%. Now, focusing on the box values in the bottom right for the 100 kilowatt and 1000 kilowatt scaled-up reactors, the fraction of heat loss due to both conduction and convection amount to 12% and 6.4% respectively. So, in order to calculate the heat loss of the system, you need to multiply your solar input by a loss fraction of roughly 2 to 7% for conduction losses and 4 to 6% for convection, depending on the size of your reactor. Therefore, in order to find the overall heat loss term in the energy balance, including both conduction and convection, the solar input needs to be multiplied by 6 to 12%. The key idea here is that if we can minimize the amount of heat loss, most of the energy can then be put into splitting the reactant molecules. This theory can be supported by the Schunk et al. Paper, since losses were minimized by optimizing reactor geometry, decreasing the size of the cavity exit, and removing the water cooling features. For example, when losses were minimized for the 10 kilowatt prototype, an efficiency of only 1.1% increased to 16.9% through these optimizations. And after increasing power to 100 and 1000 kilowatts, the efficiencies increased to 50% and 56% respectively. Therefore, minimizing heat loss and increasing power increased the overall efficiency of the system. And this is important because the more output we can get for our input, the more sustainable the process becomes, in theory. But that's a topic of a different presentation. So for now, I hope this helped you understand where the 6 to 12% heat loss term comes from in our energy balance.